Having introduced the principles of hypothesis or hypotheses, then examined different tests for testing the significance of the relationships or associations, the next stage is to test the strength of the association that we found. Remember that, of course, measuring association does not imply causality. As previously discussed, inferential statistics are divided into parametric and non-parametric tests that deal with different types of data. In this slide series, we're going to examine parametric statistical tests that we use to determine the strength of associations that we have found between variables. In brief, as summarised in slide series 1, parametric tests deal with data that is classified as scale, so that is data that is interval or ratio. Examples of that include a person's age, their income not grouped, their education attainment scores, and so on. To be parametric, data has to also be normally distributed. So having collected your data from your research, say using a survey, you will have started to explore your data using some of your basic descriptive analysis. You will then usually go about exploring each variable separately using univariate analysis, and then exploring two variables together using bivariate analysis. For basic bivariate analysis, we're usually looking at utilising contingency tables or crosstabs, and for categorical, nominal, or ordinal variables, and scatter plots for the visual representation of scale data, so that's interval or ratio. Following these initial analyses, we then want to move on to measure the strength of any relationship that we have found between two variables. To do this, we start having a look at measures of what we call measures of association. Now, for parametric measures of association, we deal mainly with what we call Pearson's R. For non-parametric, we deal with phi and Kramer's V. We then move on to explore these relationships further using inferential statistics, where we want to try and establish if the observed relationships and differences in our sample data can be generalized to the wider population. So can they be found there too? In this slide series, we're going to have a look at parametric measures of association, and in the following slide series 4b, we're going to have a look at our non-parametric measures. So the first thing, obviously, we talked about parametric, and we're going to be dealing with Pearson's R. That's going to be our measure of association we're going to have a look at. Now, it is important when we're determining whether or not the relationship between the parametric data variables you are testing is linear or not. We need to understand this. This is because only linear relationships can actually be analysed using Pearson's R. Now, scatter plots are a very useful way of visualising the relationship between two different interval variables, and so it's useful to start off by plotting that and have a look, and we can see what our relationship looks like. Now, in this example here, we can see we have a linear relationship, and it's a very strongly positive relationship. The number of different other things we can look at. So if we look at this slide series here, we can see that our scatter plot represents the top left hand shape, okay, which shows a linear relationship. We can also see examples here on the right of what we call very non-linear relationships. The one that you want to see in your data set and in your scatter plot when you plot your data is the top left hand one. So that's a nice straight line pointing upwards. Okay, so from going from small to large. If you see this, then you can actually use Pearson's R to deal with your data. Now, to explore the strength of any relationship we have found between two variables, we use what we call a correlation coefficient. Okay, correlation coefficient allows us to summarize the relationship between two variables. In the case of parametric data, the correlation coefficient that we use is Pearson's R, or its full name is the Pearson's product moment correlation. The equation on the top line shows the degree to which x and y vary together, and the bottom line shows the degree to which x and y vary separately. This is a measure of variance It's a measure of the variances that is measured by the sum of products rather than the sum of squares. We'll deal with sum of squares later. The null hypothesis, okay, is that there is no relationship in the population, and therefore any correlation that is observed is due to sampling error. A correlation, either theoretical or empirical, of 0 implies absolutely no linear dependence on the variables. A correlation of either +1 or -1 implies a perfect linear dependence of variables, and we illustrate this on the following slide. So here we can see that we have a positive correlation. Okay, so we have a positive correlation, and we can see that on the left hand one, so that's somewhere between 0 and +1, and that is characterized by x increasing as y is increasing. On the right hand one we can see that we have a negative correlation, so that's ranging from -1 to 0. So negative correlation is characterized by the reverse, so x increasing as y is decreasing. Next slide series, we're going to have a look at measures of association for parametric data.